Grandfather paradox. You've probably heard of this one, but its implications are more disturbing than most people realize. Here's the setup. You build a time machine and travel back to before your grandfather met your grandmother. You prevent them from meeting. Your father is never born. Therefore, you are never born. But if you were never born, you couldn't have traveled back in time to prevent your grandparents from meeting. So they do meet, you are born, and you do travel back in time to stop them, creating an endless loop of contradiction. This isn't just a fun thought experiment. It's a fundamental challenge to the possibility of time travel and causality itself. If time travel to the past is possible, then this paradox must have a resolution. Scientists have proposed several solutions, but each one is deeply weird. Solution 1. The Novikov self-consistency principle. The universe simply won't allow you to create a paradox. Every time you try to kill your grandfather, something stops you. The gun jams. You miss. He survives. The universe has a built-in protection mechanism that prevents paradoxes. But this implies the universe has intention, or that free will doesn't exist. Every action you take was always part of history. You were always going to fail. Solution 2. The many worlds interpretation. You successfully prevent your grandparents from meeting, but this creates a branch in reality. A new timeline where you were never born. But you still exist in the original timeline. So now there are two universes, and you've just orphaned yourself from reality. You're a traveler from a timeline that, from this universe's perspective, never existed. Solution 3. Time travel to the past is simply impossible. The paradox proves it can't happen. This is the simplest solution, but it contradicts some interpretations of relativity and quantum mechanics, which suggest closed time-like curves might exist. The disturbing part? We can't test this. We can't build a time machine to see which solution is correct. So the paradox remains unresolved, and our understanding of time, causality, and free will hangs in the balance. The Fermi paradox. If the universe is so vast, and the odds of life developing are reasonably good, where is everybody? This is the question physicist Enrico Fermi famously asked in 1950, and it's more troubling now than ever. Let's look at the numbers. The Milky Way galaxy alone contains 200 to 400 billion stars. Many of these stars have planets. Some of these planets are in the habitable zone. Even if the chance of life developing is extremely small, with those numbers, there should be millions of civilizations in our galaxy alone. Our civilization is young. We've only had radio technology for about a century. If a civilization just a few thousand years more advanced than us exists, they should have technology we can barely imagine. They should have spread across the galaxy. We should see evidence everywhere. Megastructures, radio signals, probes, something. But we see nothing. The universe appears dead, empty, silent. This is the Fermi paradox, and its possible solutions are called the Great Filter. Something prevents civilizations from becoming galaxy-spanning. The question is the filter behind us or ahead of us? If the filter is behind us, then the development of intelligent life is incredibly rare. We won the lottery, we're alone, or nearly alone. That's lonely, but it's not catastrophic. If the filter is ahead of us, then something destroys all civilizations before they can spread to the stars. Maybe it's nuclear war. Maybe it's artificial intelligence. Maybe it's climate collapse. Maybe it's something we haven't even discovered yet. And if the filter is ahead of us, we're currently racing toward it, unaware of the wall we're about to hit. Some scientists find the silence of the universe absolutely terrifying, because every year we don't find evidence of other civilizations increases the probability that the Great Filter is ahead, not behind. Or there's the ship of Theseus, an ancient Greek thought experiment that challenges our concept of identity itself. Theseus owns a ship. Over time, planks rot and are replaced. Eventually, every single plank has been replaced. Is it still the same ship? Most people say yes. It's the same ship, just with new parts. Your body replaces cells constantly. You're not the same atoms you were 7 years ago, but you're still you. But here's where it gets weird. What if someone collected all the original planks and rebuilt the ship? Now there are two ships, Both can claim to be the ship of Theseus. One has continuity of form, but new materials. The other has original materials, but a break in continuity. Which one is the real ship, or are they both real, or neither? This isn't just abstract philosophy. It has real implications for identity and consciousness. If we could upload your mind to a computer, is the upload you? Or a copy? If we could rebuild you atom by atom, would it be you, or a perfect replica? If you were teleported by disassembling your atoms and reassembling them elsewhere, do you survive the trip? Or does a copy wake up thinking it's you while you died in the disassembly? The paradox reveals that identity might be an illusion we construct, not a fundamental property of objects or beings. There might be no actual you that persists through time, just a continuous pattern that your consciousness interprets as a unified self. What makes you you? Your memories? But memories change and fade. Your body? But your body is constantly replacing itself. Your consciousness? But consciousness might just be an emergent property of brain activity, with no persistent essence. The ship of Theseus shows that identity is less stable than we think. And if identity is an illusion, what does that mean for concepts like personal responsibility, continuity of self, or even survival after sleep? Schrödinger's cat, the most famous paradox in quantum mechanics. Erwin Schrödinger proposed this in 1935 to show how absurd quantum mechanics becomes when applied to everyday objects. Here's the setup. You put a cat in a sealed box with a vial of poison, a radioactive atom, and a detector. If the atom decays, the detector triggers, breaks the vial, and kills the cat. If it doesn't decay, the cat lives. Quantum mechanics says that until you measure it, the atom exists in a superposition of states, both decayed and not decayed simultaneously. Therefore, until you open the box and look, the cat is both alive and dead. Not just unknown. Actually both. Existing in multiple states at once. When you open the box, the superposition collapses. The cat becomes either definitively alive or definitively dead. But until that moment, it's genuinely both. This seems insane because we never see superposition in everyday life. You've never seen a cat that's both alive and dead. But quantum mechanics insists this is how reality works at small scales. So why don't we see it at large scales? This is called the measurement problem, and it's one of the deepest unsolved mysteries in physics. Several interpretations exist. Maybe consciousness collapses the wave function. The act of observation by a conscious being forces reality to choose one state. But this implies consciousness has special physical properties, which seems unlikely. Maybe the universe splits into multiple realities every time a quantum event occurs. In one universe, the cat lives. In another, it dies. Both are equally real. You just happen to be in one of them. This is the many worlds interpretation, and it's completely serious physics, not science fiction. Maybe the cat is never actually in superposition, and our understanding of quantum mechanics is incomplete. There might be hidden variables we can't detect that determine the outcome in advance. We don't know, and after nearly a century of quantum mechanics, we still don't have a universally accepted answer. The cat remains both alive and dead, and so does our understanding of reality. The EPR paradox. Einstein-Podolsky-Rosen proposed this in 1935 to show that quantum mechanics must be incomplete. They were trying to prove quantum mechanics wrong. Instead, they discovered something even stranger. Here's what they found. Quantum mechanics predicts that two particles can become entangled. Once entangled, measuring the state of one particle instantly determines the state of the other, no matter how far apart they are. Even if they're on opposite sides of the universe. Einstein called this spooky action at a distance and argued it couldn't be real because it would require information to travel faster than light, violating relativity. So either quantum mechanics was wrong, or there were hidden variables we couldn't see that predetermined the states of both particles. In the 1960s, physicist John Bell figured out how to test this, and the experiments have been done over and over with increasing precision. The results are clear. Quantum mechanics is right. Entanglement is real. There are no hidden variables. When you measure one particle, the other particle instantly responds, even across vast distances. This has been confirmed so many times, it's no longer controversial among physicists. But how? How can information travel faster than light without violating relativity? The answer is, it doesn't count as information in the way relativity prohibits. You can't use entanglement to send messages faster than light, but the correlation is real and instant. Reality is non-local. The universe is fundamentally connected in ways that violate our intuitions about space and time. Things that appear separate aren't actually separate. Distance might be an illusion. Two entangled particles aren't really two separate things. They're one system, no matter how far apart they appear to be in space. This suggests the universe might be fundamentally holistic. Everything might be connected to everything else at a quantum level. Separation and locality might be convenient fictions our brains use to navigate reality, but they're not how reality actually works. The twin paradox. One of Einstein's relativity predictions that seems logically impossible, but is absolutely real and has been measured. You have identical twins. One stays on Earth. The other gets on a spaceship and travels at near light speed to a distant star and back. When the traveling twin returns, she's only aged a few years. But her Earth-bound twin has aged decades. They're no longer the same age. This is time dilation, and it's been confirmed countless times with atomic clocks on airplanes and satellites. It's real. Time genuinely passes at different rates depending on speed and gravity. But here's the paradox. From the perspective of the traveling twin, she's stationary and Earth is moving away. So shouldn't Earth's twin be the one who ages slower? This is where the paradox comes in. Both perspectives seem equally valid, but they predict opposite outcomes. Who's actually younger? The resolution. The twin paradox isn't actually a paradox once you factor in acceleration. The traveling twin experiences acceleration when turning around to come back home. This acceleration breaks the symmetry. There's a real difference between the twins' experiences. The twin who accelerates is the one who ages less. Acceleration creates a real asymmetry in space-time. But this answer reveals something disturbing about the nature of reality. Time isn't universal. There's no cosmic clock ticking the same for everyone. Your personal experience of time depends on your motion through space. Time is relative, and simultaneity is an illusion. Two events that are simultaneous from one perspective might happen years apart from another perspective. The concept of now happening everywhere at once in the universe is fundamentally wrong. There is no universal present moment. Your now and my now might be different slices through space-time, and both are equally valid. The bootstrap paradox, also called an ontological paradox or causal loop. This is where an object or information has no origin. It simply exists in a loop. Here's an example. You receive a book from your future self. You read it, memorize it, and years later, you travel back in time and give the book to your past self. Where did the information in the book come from? It didn't come from you because you got it from your future self, but your future self got it from their past self, and so on, forever. The information has no source. It exists in a closed causal loop with no beginning. This gets even weirder with an example. A composer from the future travels back in time and gives Beethoven a symphony. Beethoven publishes it as his own. The future composer grew up listening to this Beethoven symphony, learned it, then traveled back and gave it to Beethoven. Who actually wrote the symphony? No one. It came from the future into the past and then existed. It has no creator. This paradox suggests that if time travel to the past is possible, information and causation might work in completely counterintuitive ways. Effects can precede causes. Things can exist without creation. The universe might contain information that was never actually invented by anyone. Some physicists take this seriously. If closed time-like curves are possible in the universe, then bootstrap paradoxes might be real features of reality. Information might be able to exist without a source. Causation might be circular, rather than linear. The Banach-Tarski paradox. This one breaks mathematics itself. It states that you can take a solid sphere, cut it into a finite number of pieces using only theoretical cuts, then reassemble those pieces into two complete spheres, each the same size as the original. You start with one sphere. You end with two identical spheres. You haven't stretched or added anything. You've just rearranged the pieces. You've doubled matter through pure geometry. This seems impossible. It violates conservation of mass. It violates common sense. But it's a proven mathematical theorem. In the abstract space of mathematics, this is absolutely, definitely true. Why can't we do this in reality? Because it requires cuts of infinite precision and deals with infinite sets of points. Physical matter is made of atoms, which are discrete. You can't actually make the required cuts in real material. But the fact that mathematics allows this reveals something disturbing. The math we use to describe reality contains possibilities that reality itself doesn't. Either our mathematical models are more expansive than reality, or there are aspects of reality we don't yet understand where something like this might be possible. The Banach-Tarski paradox also reveals deep strangeness in set theory and infinity. When you're dealing with infinite sets, normal rules break down. You can split infinity into two infinities, each as large as the original. Infinity plus infinity equals infinity. These aren't just mathematical curiosities. They suggest that infinity, if it exists in reality, behaves in ways that completely violate intuition. Olber's paradox. If the universe is infinite, eternal, and filled with stars, why is the night sky dark? Think about it. If there are infinite stars, and they've been shining forever, then every direction you look should eventually hit a star. The entire night sky should be as bright as the surface of the sun. But it's not. It's mostly dark. This paradox troubled astronomers for centuries. The resolution came with the discovery that the universe is expanding and had a beginning. The universe is not infinite and eternal. Stars haven't been shining forever. The universe is only about 14 billion years old. Light from distant stars hasn't had time to reach us yet, and the expansion of space means the most distant light is stretched into wavelengths we can't see, redshifted into invisibility. So the darkness of the night sky is evidence for the Big Bang. The fact that we see darkness proves the universe had a beginning. But this resolution itself is troubling. It means the universe will eventually die in heat death as stars burn out and no new ones form. The darkness we see is a preview of the universe's ultimate fate. Eventually, all stars will die. All matter will decay. The universe will be cold, dark, and dead forever. The night sky is dark because the universe is young and still alive. But it won't stay that way. In the far future, any civilization that still exists will look up and see nothing but darkness. No stars, no galaxies, just endless black void. And they'll be the last witnesses to existence before everything ends. The information paradox. Stephen Hawking discovered that black holes emit radiation and eventually evaporate. But this creates a paradox that challenged the foundations of physics. When something falls into a black hole, it carries information. The exact quantum state of every particle. According to quantum mechanics, information can never be destroyed. It can be scrambled, but it must always exist somewhere. But when a black hole evaporates, where does the information go? Hawking radiation is thermal and random. It doesn't seem to carry the specific information about what fell in. So either information is destroyed, violating quantum mechanics, or the information escapes somehow, violating our understanding of black holes and general relativity. This paradox consumed the last decades of Hawking's life. He eventually conceded that information probably isn't destroyed, but we still don't fully understand how it's preserved. Recent theories suggest the information might be encoded on the event horizon itself, holographically. The black hole's surface might contain all the information about its interior, like a hologram encoding three-dimensional information on a two-dimensional surface. Or maybe the information escapes through Hawking radiation in a way we don't yet understand. The radiation might be subtly correlated with what fell in, preserving information even though it appears random. But the paradox remains one of the deepest problems in theoretical physics. It reveals a fundamental incompatibility between quantum mechanics and general relativity. One of them is wrong, or incomplete. And until we solve this paradox, we won't have a complete understanding of reality. The paradox also suggests something profound about information. If information truly cannot be destroyed, then every quantum state that ever existed still exists somewhere in the universe. The past might not be gone. It might be encoded in the structure of spacetime itself. Nothing is ever truly lost. 10 paradoxes. 10 fundamental contradictions in our understanding of logic, physics, causality, and reality itself. Some may eventually be resolved. Others might be unsolvable, revealing permanent limits to human understanding. But here's the truly disturbing possibility. What if these aren't paradoxes at all? What if reality genuinely is contradictory? What if the universe operates on rules that don't have to make sense to us? What if logic itself is just a human construct that reality isn't obligated to follow? These paradoxes might not be problems to be solved. They might be windows into a reality that's fundamentally stranger than anything our evolved brains are equipped to comprehend. We evolved to hunt animals and avoid predators on the African savanna. We didn't evolve to understand quantum mechanics or the nature of time. Our intuitions fail at the extremes. Maybe the universe doesn't care about human logic. Maybe contradictions are features, not bugs. Maybe reality is weirder than we can possibly imagine, and these paradoxes are just the tip of the iceberg. This is Detective Vera Nash, closing the case files on the impossible. If you want to investigate more paradoxes that challenge reality itself, subscribe to this channel. We post daily investigations into mysteries that break the rules of everything we think we know.